So for the physiological model, there is so many steps before reaching that equation. But as we are just talking about the concepts here, rather than why we reach this point, we will talk a little bit in the second part about one side of this equation. But at this stage, I want to show you one physiological model of the volume distribution, aberrant volume distribution, which is called in your clinical textbook as just V, equals the volume distribution of the plasma plus the volume distribution of the tissue multiplied to the fraction unbound free in the plasma over the fraction unbound in the tissue. Okay? So, those factors, all of those factors would affect the final volume distribution that we have. Okay? So, we will have examples before going into examples, calculation examples, before going into examples of the drug or plasma protein binding effect or disease effect on the final volume distribution measured. So let's go with the first one. If we have phenytoin has a fraction of unbound fraction unbound in the plasma of 0.1. This is unbound in plasma, okay, and a fraction unbound in tissue of 0.2. So this is unbound in tissue. And now that we have a 70 kg person, that the plasma volume in the plasma equals 5 liter and volumes in the tissue equals 80 liter. What is the drug volume distribution? And again, you can just use this direct substitution. We have volume of distribution that is equal volume in the plasma plus volume in the tissue multiplied to unbound in the plasma over unbound in the tissue, which will be equal to let me just because the picture keeps. So we have fraction unbound in the plasma that is equal to 0.1, fraction unbound in tissue that is equal to 0.2. We have volume of plasma, volume of the tissue. This is 5 liter and this is 80 liters. Okay. And then it's volume distribution. This would be equal volume of plasma plus volume of tissue multiplied to this fraction, which is unbound in plasma over unbound in tissues. Okay, this would be equal to 5 plus 80 multiplied to 0.1 over 0.2, which is half. Then this would be equal to 45 liter. Okay, this would be the estimation of the aberrant volume distribution according to those factors. Okay, what would be the drug fraction unbound in the plasma increases to 0.2? Imagine that the changes of the fraction from 0.1 to 0.2 only, which is 0.1 difference, okay? What happens to the volume distribution? So if this is A, if this changed to 0.2, okay, then accordingly volume distribution would be equal to 5 plus 80 multiplied to 0.2 over 0.2, which is equal to 85 liter. Imagine the difference, and it's the fraction unbound increases. It's common sense as the fraction unbound in the equation increases by not differences in other factors, which would cause an increase in volume distribution. Again, all other factors are the same, okay? Then, if the drug kinetic can be described as one compartment model, what is the effect of changing the volume distribution you will have on initial concentration and loading dose? Okay, so if you consider that the initial concentration is your loading dose or the dose over VD, and we know that we have an increase in the volume distribution. This increase in the volume distribution would cause a measured initial concentration that is lower than expected, right? Lower than the first case, for sure. So accordingly, this would need an increase in the dose that is taken, okay, to reach the concentration that we needed, okay? Okay, and from this slide on, we will talk about different cases of the effect of different factors on the final measurement of the aberrant volume distribution. So in here, we will start with the plasma protein binding and then drug interaction. We have valproic acid administration and its effect on the volume distribution of phenytoin. We are not changing the volume of distribution of the plasma or the volume of the tissue. So those two factors are the same. Both phenytoin and valproic acid are highly protein bound, approximately 90% of the same site, which is albumin, okay, and plasma albumin, and they are administered together. The protein binding of phenytoin is reduced from 90 to 80. So the fraction bound is less by 10%, okay, and then accordingly the fraction unbound, unbound in the plasma is increased, okay. So the fraction unbound in the plasma increased, okay, and I'm just telling you that, which you know that this is a displacement or competition, which we already know that is one of the major causes of drug-drug interaction, okay. And this is what will happen if you are talking about volume distribution, and then this is not changing, and nothing happened to the tissue, the free drug or unbound drug in the tissue, and we have an increase because of the displacement or competition and the fraction unbound in the plasma, then accordingly the total volume distribution would be expected to increase. And we could have the same thing, the same idea using numbers, but I'm just talking about concepts here, okay? And this case, the first case, again, we were talking about what? Plasma, okay? Plasma protein binding. And in the second case, we are talking about tissue binding, in which we are talking about the how much the fraction free or unbound in the tissue is affected. In this example, we have the effect on the volume distribution of digoxin by quinidine, okay? And again, I don't care about the names of the drugs or what affects what, but I want you to understand the concept. So if I ask you about anything that is related to this equation, which is the physiological model of the aberrant volume distribution, you can know what is the expected effect at the end, okay? And if we have more than one factor affected, we need to take into consideration the whole equation and to see if it's increase or decrease according to the difference in each factor. Again, in here, the volume of the plasma and tissue is not changing. The digoxin is not that much bound to plasma protein. It's negligible, but it's we have 70 to 90% of quinidine bound to plasma protein and alpha glycoprotein. As the drug of interest is not that much bound to plasma protein, then we need to take into consideration other thing, right? Digoxin is extensively bound to cardiac muscle tissue, when we compare it to the plasma concentration, which is 70 to 1, which is a major point. Concomitant administration of quinidine decreases the binding of digoxin cardiac and the cardiac muscle tissue. So the effect won't be here, won't be here, and won't be here, but it would be here. And this is what I'm showing you. So the increase Anyway, the increase, we have it in the unbound in the tissue, which would cause a decrease in the total volume distribution, apparent volume distribution that we are expecting, okay, of the drug. If we are talking about the effect of the disease state, again, the effect of the disease state on the volume distribution, we're talking about one disease effect, which is renal failure. On the volume distribution of phenytoin, we are assuming again that the volume of the plasma and the tissue is not changing or is not affected, so they are constant. And phenytoin is highly bound to plasma, in plasma to plasma protein, so it's highly bound to plasma albumin. 90% is bound to albumin. And we said that the disease state would affect the status, either physiological or pathological. We have effect on the status of the body. One of the major effects of the renal failure, we have decrease in the albumin. Okay, so the amount, the quantity of the protein, concentration of the protein is what affected, and we have decreased in the affinity, which is, again, we said the relationship of what we have between the protein and the drug is decreased. So if the affinity is decreased and the concentration of the albumin decreased, and we are talking about plasma albumin, so accordingly we have more free drug, right? The tissue free concentration or fraction is not affected, so accordingly we are expecting increasing in the volume of distribution, total volume distribution. If we are talking about digoxin, which is mainly and the again mainly bound to tissue protein rather than plasma protein, if we are considering the same thing, that the plasma volume, tissue volume is not affected, in addition to plasma free fraction, we need to know what the renal failure would affect the protein of the tissue that we are interested. It causes a decrease in the binding, which means that we have more fraction unbound or free in the tissue, which is the cardiac tissue, which causes a decrease in the volume of total volume distribution. So it's a conceptual way of looking to the total volume distribution, apparent volume distribution, taking into consideration different factors that we were not talking about before, because we were not talking or considering the protein binding before. I'll stop here and I will continue in the next